we're going to take again a bit of a departure from the math side of things and describe this concept of statistical significance. Happens all the time in the literature, as a matter of fact, in the research literature. As a matter of fact, researchers like to say, well, we found a statistically significant association or a statistically significant difference between the means, or these findings are statistically significant. And it's almost like they're throwing up the shield when they're trying to present an argument by going, well, we've shown statistical significance here. What do you have to say to that? And it's important to know what statistical significance means, because it is important. But what's also important as well is, the meaningfulness that we find in statistics. And this is a bit of a preamble. Sometimes we can find things that are statistically significant, but in the real world have very low. It's not that meaningful. And I know that's a little bit weird. Aren't you saying, well, I mean, isn't statistical significance important? It is. So aren't the differences and associations important? So some key learning goals here, and I mentioned this last week, where we're going to look at probability values. So probability values fall into statistical significance, and you might see a little bit of repetition. That's okay. We will get into something called what we call setting the alpha value or the alpha level. Researchers do this when they are trying to set up their framework for answering a research hypothesis. And we have to have some sort of threshold that we have for the probability of things occurring. And so this is what your alpha level is. We'll understand and define what statistical significance means, and then there's that point about the meaningfulness of differences or meaningfulness of associations. And then at the very end, we're going to get into this thing called the concept of a type 1 and type 2 error. I think it's fairly clear, but I think when students first encounter this, they kind of go, what was this again? Hopefully I'll be able to explain it to you in a way that is clear and understandable. So we know that in research, and I've said this before, we often take a look at associations between variables and differences between variables, differences between two groups. I might measure the same group twice or three times on certain variables and measure those differences or associations. There's all different ways that we engage in research. Researchers are primarily interested in relationships or differences or other things that are statistically significant. If you have to pay attention to see this, and you need to read a lot of journal articles to see this, but if you ever read a journal article all the way through and you get to the discussion section and you begin to read the discussion, you'll notice something, that the researchers only talk about the findings in the discussion that were statistically significant. They don't talk about the ones that weren't. Right? That's not of interest to them. Here's what we found that was statistically significant. They may acknowledge or they may try to explain some non-significant findings, but generally that's not what happens. What they do talk about are findings that were statistically significant. So what does this term mean? We need to unpack this. And how can we recognize it when we read it in journal articles? How do I know when a researcher presents some numerical findings to me in the results section that those findings were statistically significant? And so I did describe this earlier last week, and I said I would come back to it. So hopefully I kind of left you hanging a little bit. And we described statistical significance last week as this: any difference or any association between groups that is not due to chance, but due to some systematic influence, i.e., the intervention or the independent variable that was applied. Okay, so this was something from the outside that was applied to a sample, and this, whatever this something was, it elicited a change in a value. And when I see changes in values, I want to know that those values actually happened because of this influence. And we talked about that before. And so that's what statistical significance is. Differences we see in groups or associations that didn't happen by chance, but were likely due to some sort of external influence. We have to express statistical significance, right? We can't just say, well, these two, what we found here was statistically significant. We actually have to unpack what we're saying here. And so we can express statistical significance as this: the degree of risk that the researcher is willing to take, that the researcher rejects that things happen by chance when they actually did. Okay, so there's always a chance that the researcher made a mistake. That is, at the end of the day, after they ran the experiment, they came out, they saw this, they ran their machinations, and they come to this conclusion. And they said, well, we found a statistically significant finding here. There's always the chance that the researcher was wrong. And so the researcher has to acknowledge the fact that they could be wrong. And so they express statistical significance as some sort of value or degree of risk. That's forthcoming in the next number of slides. So this level of risk that the researchers have to state is actually set up before they even run the experiment. So they set up ahead of time. They go, you know what? Here's our minimal threshold that we're going to accept as a level of risk that the findings happen by chance. Okay, and anything less than this level of risk, we're going to go and take the opposite or the alternative hypothesis and say that this intervention or this external influence is what caused this change in the variables. And so the term for that is a priori, right? Ahead of the fact, right? Before the fact, this is what we're going to set up. And so what the researcher does is they eliminate some level of bias from that. They say, no, here are the rules that we are going to play by, and we're not going to break these rules. And so the standard or level of risk is called the level of significance, and it's called the alpha level. Okay, so for those of you who are going off into graduate school, if you do run an experiment, those of you who are taking an honors thesis, and you're going to run an experiment statistically, you have to set ahead of time what your alpha level is, or your level of risk for statistical significance. Okay, you're not going to see alpha level a whole lot in research journal articles that you read. You'll see it expressed differently. They'll just say the level of significance, or the level of significance was set at. They may not necessarily use the term alpha. So this is kind of more of a textbook term. But nevertheless, every researcher does this. They come out and they say, here's our level of risk that we are going to take in terms of making our statistical decision. And so this level of significance, again, can be viewed as the probability of rejecting that chance was the cause of the result when it actually was. Okay? And so at what percent chance do we go, you know what, the chances of what we found here happened by chance is so small that really, you know what, it's likely the alternative hypothesis that was the case, that caused this change in the variable, that caused these findings to occur. So we need to take a look at how low do we go for that percent chance. So these levels of risk generally, for the most part, I don't think I've ever seen anything other than this, are set quite low, right? And they're usually set between 0.01 and 0.05. So when you read a journal article, you should see in the methods section, level of significance was set at, and you'll see one of these two values. Normally you're going to see the level 0.05. Okay? So now when we set the level of significance at 0.05, this is what we mean. This is our threshold, okay? What we're saying is this. When we set our level at 0.05, we say this: whatever the findings are, there is a 5% probability that what we see happening here, differences, associations, right? It's due to chance and not due to the intervention or treatment. This is our threshold. Whatever we see happens in the experiment, right? We run the experiment. Here's all our data. Now we're looking at associations or differences. We are saying this ahead of time. There's only going to be a 5% chance the differences or associations that we see happen by chance. Anything less than 5%, right? Anything less than 5% probability, we have to accept the alternative explanation, i.e. my intervention, i.e. this external influence caused these findings. So journals express these statistically significant findings as this. The research author might say this: the findings were significant or statistically significant at the 0.05 or 5% level. They'll state that. And so what they're saying is the findings we saw here, less than a 5% chance they actually happened by chance. And so we're going to be accepting the alternative explanation. And you'll see this in the research journals expressed as a probability or a p-value. So the probability that something happened, right? And they're going to give you a decimal. And the decimal tells us the percent chance the findings happened by chance, right? So, and you're going to see this often conventionally said as either p less than 0.05, p less than 0.01, p less than 0.001. You'll see it as here's some values, here's some numbers, and then beside it you'll see one of these. And what the author is telling you is that you see these two things that happened here, the differences between the two scores? Yeah, well, there was less than a 0.05 chance that this happened by chance. And so we're going to accept the alternative explanation. That's what the research authors are saying. You might even see some values here, and beside it, you'll see p less than 0.001. And what the research author is saying there is, yeah, you see these values here, the association between these two values here. Well, there's less than a 0.1% chance they happen by chance. And because the researcher said this ahead of time, we're willing to accept, right? We set our level of significance at 5%. Because these things are much less than 5%, we can't accept that chance caused these values. We have to accept the alternative explanation. So where does this p-value come from? I mentioned last week that you will never have to calculate a p-value. Okay, you're not going to have to do that, because some students go, do we have to do this? You don't. This is the wonderful thing about SPSS and other software packages. They do that p-value calculation for you. Okay, so you don't have to worry about that. You don't have to worry about that. So let's just give an example here. Let's say that you ran a t-test and you came out with this, and you look for differences between two means, and the SPSS came out and gave you a p-value of 0.009. SPSS will do that. They will give you a direct or a very clear and concise probability value. They're not going to say less than 0.05 or less than 0.01, right, our levels of threshold. They're going to give you a p-value, and then you're going to compare the calculated p-value that came out to your threshold, right? So if you'd set your threshold at 0.05, that is to say anything, if a p-value gets pumped out by SPSS and it's anything less than 0.05, we're going to accept that something else other than chance caused this difference or caused this association, right? We have to go to the alternative hypothesis. So in this case here, if SPSS gave me a p-value of 0.009, but my threshold was 0.05, I know that 0.009 is much less than 0.05. And so what we'd say then is we would say, yeah, you know what? There's only a 0.9% chance that the findings happen by chance. I'd set my threshold at, I'm willing to accept a 5% chance things happen by chance before I'm going to reject it. 0.9% is much less than a 0.5%, right, chance of things happening by chance. And so we're going to say, you know what, I don't think chance caused this difference or association. Likely it was due to something else. We're beginning to see a pattern here, and it's this. The smaller the calculated p-value, the less likely the findings happen by chance. Okay, so a smaller p-value is what researchers like to see because it shows that there's a strong likelihood that their alternative hypothesis was true, and the null hypothesis, right, there were no differences between the means or no association, is not the case. Okay, so when the alpha value has been set at 0.05, and you'll see that in the literature, and the calculated p-value from SPSS or another software package is less than 0.05, the result is statistically significant. And so here's a couple of examples here. Example 1, researcher sets the level of significance at 0.05. The SPSS calculates a p-value of 0.02 for whatever variables that researcher is interested in. Okay, 0.02 is less than 0.05, and so the researcher comes out and says the findings were statistically significant. Whatever we found likely didn't happen by chance. As a matter of fact, the researcher can say specifically the chances that the findings happen by chance are only 2%, and that's much less than what I set my threshold at, which is 5%. So therefore, I'm not going to accept the null hypothesis as the case. Remember we did that before? We said before the researcher sets up the null hypothesis that things could have happened by chance and there really was no difference between the means. That's exactly what's going on here. The researcher wants to be clear that, yeah, the null hypothesis isn't the case, so I'm going to set my threshold at 5%. When SPSS tells me there's only a 2% chance the findings happen by chance, I'm not going to accept the null hypothesis. I'm going to accept the alternative hypothesis and say that some sort of other influence cause these findings, different scores or association scores. Now, sometimes the p-value is much higher than 0.05. Right, we haven't talked about that yet. What happens when the p-value is higher than 0.05? So here's my second example. I set my level of significance at 0.05. SPSS runs a test for me and comes out and says, yeah, the p-value for your association test here is 0.12. Okay. Now 0.12 is much larger than 0.05 and actually is above my threshold, my minimal threshold that I'm going to take to say that the findings happen by chance. It's much higher. Now what SPSS is telling me is that, you know what, Mike, these values here that you have, there's a 12% chance this could have happened by chance. What do you think about that? Well, I already know what I think about that because I said no. I set a threshold of a 5% chance that things happen by chance. Anything less than 5%, I'm going to say that the findings didn't happen by chance. The fact that there's a 12% chance the findings happen by chance, that's much higher than my threshold. And so I'm going to say this: the findings are not statistically significant. As a matter of fact, I have to accept the conclusion there's too much of a chance the findings could have happened by chance. 12% is higher than 5%. So I have to say, yeah, you know what? The findings here likely happened by chance and not to some sort of external influence. That is to say, my intervention or my alternative hypothesis that I was trying to test. This is just an example of what you might see in the literature. So this is, here's some of the results here in this finding. It had to do, so the finding, this came from this journal article here, a recess intervention to promote moderate to vigorous physical activity. So here we go. So what's one of the findings here? Moderate to vigorous physical activity during recess increased significantly in the intervention school children from 6.9 plus 0.8 to 14.9 plus or minus 0.09 pre and post intervention. And here is where you see the p-value. They're saying here the chances that these two values occurring, this difference score here, the chances that this difference occurred is less than 0.01%, right? Because I can convert 0.0001 to a percentage. I simply move the decimal to the left 2 places. Only a 0.01% chance that the findings here happen by chance, okay? So then we would say that, yeah, it was likely due to the intervention here, right? When I introduced whatever the intervention was, moderate to vigorous physical activity increased significantly, okay? There's another example here in school. Moderate to vigorous physical activity also increased significantly more for intervention compared to control children. And again, they've got a value here. the values are 14.4 versus 3.3. Well, that's a pretty big difference even in of itself. But again, we still have to look at the p-value. What are the chances that the different scores here happen by chance? Well, the p-value comes out and says 0.014, and that means there's only a 1.4% chance that these differences here happen by chance. And so likely it was due to the intervention that the author was using. I want to take you in behind the scenes a little bit, and this is my way of trying to explain to you what SPSS is doing, at least with respect to significant differences between two means. Association ones are much more challenging to show on a PowerPoint slide. But I use the concept of significant differences or non-significant differences as an example because it's probably the one that's most easily for us to kind of sink our teeth into. So here's an example of what is happening, and I'm drawing in now the normal curve. I have to draw in the normal curve here because the normal curve is all about probabilities, and statistical significance is all about probabilities. And so I want to take these two worlds and collide them a little bit. So here's an example. We'll call it the tale of two patient groups, right? So here I've got on the left-hand side, I've got the normal curve of patients who have no disease, okay? And on the second, I've got another curve here, and I've got patients with disease. And whatever it is I'm measuring them on, whatever these values are, right? Let's say it's pain. So let's just say that I'm measuring, this might be the test results units down here is pain. And so I measure pain scales in patients without the disease, and they may get a value of 17, whatever the score is. Maybe the score is out of 50, okay? So from 0 to 50, what is your pain score? And so we have individuals here who might be scoring somewhere around about a level of 17 on the pain score. Right. Now, we know that we don't just take a look at the means, we also take a look at the distribution of the scores because it's a continuous variable, right? And so there are very few patients here in the sample have very, very low pain, and very, very few patients over here on this side here have pain that is much higher. Most of the patients without the disease, when you ask them about their pain, are somewhere in the middle, round about 17. We know that. Now, what if I was looking at the differences between pain between patients without the disease and patients with the particular disease? Now, I'm measuring them using the same pain scale, and here's what we find. We find that the patients with the disease here have a much higher level of pain on average than the patients without the disease. We also see the spread of scores here with patients with the disease. Look at this. This gets really interesting. Look, there are some people who have the disease who have lower pain scores than patients who don't have the disease. So we actually see a little bit of overlap here, right? So there are the chances now that patients with both the disease and without the disease can have similar pain scores. And this is what makes it a little bit complicated now when we're trying to say, well, we think that, and our hypothesis is, patients with the disease are going to have higher pain scores than patients without the disease. And we have this little area in here that kind of gets it a little bit confusing. Now, when we take a look, we actually see there's a substantial difference in between the two in terms of their mean pain scores, right? Because again, in statistics, we look at mean scores. As a matter of fact, we see that the patients with disease on average have a pain score of roundabout, looks like 35 compared to say the 17, and so their pain scores are double on average. And even more so, we've got a bunch of folks over here who are in severe pain. But again, we also have some folks down here who have, they still have their pain, but again, it's not as high, right? I mean, you've got some people here who have the disease, who have pain scores that are actually lower than people who don't have pain. So it's a bit of a quandary. How do we know that these two means are statistically significantly different? If this is what our hypothesis is, our research hypothesis is, yeah, patients with the disease are going to have higher pain scores than patients without the disease. And if we take a look at the overlapping normal curves, right now it looks like, yeah, there could very well be the case. But this could also happen And so perhaps another way of saying this is this question, right? How far apart do the means of the two samples have to be before we can say there is a statistically significant difference between the two means and accept our research hypothesis that, yeah, pain scores are significantly higher if you have this disease compared to if you don't? That becomes the question. But another way of asking the question is this: what are the chances, the probability, that the difference that we see between the means in terms of the pain scores, right, are due to chance rather than the disease itself in this case? So this now becomes the null hypothesis, right? Did these two different pain scores, despite the fact that they're actually quite different by, and one is double the size of the other, did this happen by chance or not? How does SPSS work to show us this? Things get a bit tricky now in terms of explaining what is going on, so please bear with me. And I want you to not pay attention to the titles. We'll come up to the null hypothesis a little bit later on, and we'll talk about this a little bit later on here. Here's what I want to do. What I've done on this slide here is I've given you the normal curve, or the spread of the scores for patients without the disease. Here's the mean value that's sitting in the center here. And again, on the bottom, this is level of pain. And I think the mean was around about 17, right, if I recall correctly on the previous slide. So what does this tell us about the individuals who don't have the disease and their levels of pain? Well, again, it tells us, the normal curve tells us that very few have very, very low levels of pain, but very few have very, very high levels of pain. Okay, most of the individuals have this level of pain, which is somewhere in the center here. That's where most of the values are. Remember, we talked about that. About 68% of all the values of pain fall around the value of 17. If I go one standard deviation above the mean and one standard deviation below the mean, that's almost 70% of the individuals kind of fall in the center. There is a small chance, however, very small chance, that 5% of the individuals are going to have pain, they're going to have really, really high values of pain. And so there's this line here, and this is the 5% line. Now, I don't know what Z-score that is. I'd have to go and take a look again at my Z value. It doesn't really matter. Right now, all we have to know is that in the patients without the disease, a small percentage, right, 5% of them are going to have high levels of pain. Now, that's the very same thing that we said before about the patients with the disease. We figured that patients with the disease are going to have high levels of pain. But we also know that patients without the disease, a very, very small percentage of them are going to have high levels of pain as well. And so this is this 5% value here that we're going to set as our level of significance. In other words, this is a very small chance that people who don't have the disease have very high values of pain. Okay, a very, very small percentage of them, a very small probability that if you don't have the disease, you're going to have high levels of pain, right? There's a less than a 5% chance that your pain value is going to end up in this category here on the higher end if you don't have the disease. Okay, that's setting some things up here. Let's go to the next slide and extend this a little bit further. So what researchers do when they set their level of significance is they say something like this. Here's my mean score for my patients without the disease. What are the chances that someone without the disease is going to have a very high value of pain? Well, they know that the chances are very, very small if we set it at 5%. Look, there's hardly anybody who, without the disease, has very, very high levels of pain. And so they may say, well, we're going to set our level of significance as 5%. That's what they're going to do. Now, they could set it at 1% if they wanted to, which would be a little bit further here, but right now, conventionally, it's going to be set at 5%. So what does this mean? This means if I overlap two spreads of scores, right, patients without the disease and patients with the disease, if the mean of the diseased patients, if I were to put an overlap here, I'm going to do that on the next slide, if the mean of the diseased patients in terms of their pain scores fell to the right of this critical value or this threshold of value, we would then say that there's less than a 5% chance that that second mean right? The second mean happened by chance and was more likely due to the disease. That's what we are saying. We're saying, yep, because so few people without pain have such high values of pain, it's highly unlikely that if I see another mean and another mean falls within this range, it's so unlikely they didn't have the disease, it's likely that their pain scores were due to the disease. And so a lot of times when we get to with t-test scores, what we do is we compare overlapping normal curves, and the threshold values that we set are based upon the normal curve value as well, probability and proportionality, right? And so this is what we do. We set this threshold value of here, and we say that if I overlap another normal curve of individuals who have the disease and I measure their pain, if their mean value of pain falls within the shaded area, we then say, yeah, the chances of that happening simply by chance are too small. It's less than 5% that mean pain value of those with the disease fell here, so therefore we're going to accept the alternative explanation, and that these higher pain scores in that second group with the disease was caused by the disease and didn't simply happen by chance. What I've set up here is two scenarios, again using the same example of pain scores between patients without a disease and patients with the disease. And I'm going to show you the difference where we've got, in a situation where there's no statistically significant difference and a situation where there is a statistically significant difference. So just setting this up again here. Here we have the normal curve of patients without the disease. There's their mean value, which we said was a raw score of around about, say, 17 on that pain scale. And here's our level of threshold here, 5%. This is our level of significance. Right, and so what we want to do is superimpose the mean of the, and I can't put the normal curve, I just can't do that with the PowerPoint. I'm just going to show you the mean. We're going to superimpose the mean on top of a mean of pain values from a group of people with pain onto those of the patients without the disease, and see where it falls. Is it going to fall to the right of our threshold, or is it going to fall to the left? Well, if it's not significant, if there's no statistical difference between the two means, it's going to fall to the left of our 5% threshold. This might be a pain value of 25, and even though there's a difference of, say, 8 points, if our mean pain score is 17 and this is 25, even though we see a difference of 8, the chances of that value of 25 occurring is quite high. As a matter of fact, if you add up all the area under the curve and turn that into a probability function, that might be a 23 or 24% chance this mean of pain scores in patients with the pain fell here. Our conclusion would be, yeah, the chances of this pain score happening by chance is so large, likely there really is no difference in pain scores between people without the disease and patients with the disease. On the flip side, over here, if we take a look at the pain scores of patients with the disease, we see it falls to the right of our threshold. And it's very, very small. This might be in the 1% category over here. We also notice there's a large value of difference in terms of raw scores between pain scores. If this was 17, this might be a value of 42. So now we've got a difference of 17 points. But the point is this. We see this mean happening here, and what the researcher is saying is this. These individuals here say they have pain, and this is their pain scores. It's highly unlikely they don't have the disease. Why? Because only probably about 1% of all the folks here, if I'm trying to, this is 5%, this is probably closing in on 1%. There's only a 1% chance a patient without the disease is going to have this high of a pain score. And so likely these high pain scores are actually due to the disease, and the differences here don't happen by chance. We're going to shift into something a little bit different here, and it's this linkage between statistical significance and the null hypothesis. In particular, we're going to get into the discussion of making mistakes in research, and we call those type 1 and type 2 errors. And if you've been reading along and hanging on, hopefully, more than simply by your fingernails so far, with respect to statistical significance and chance, you might have thought that, oh yeah, this whole aspect of things happening by chance, we saw that before, when we describe the null hypothesis. So let's take a look at these two things here. I'll probably go through these slides fairly quickly. Type 1, we're going to get into type 1 and type 2 errors, and I just want you to recognize the potentiality of these things happening. So when we set up our level of significance, right, and here's an example. If I've got a calculated p-value, let's say it's 0.024, SPSS gives me this, and it's less than our threshold that we set up at 0.05, we say that there is a statistical difference between the two means, right? We've established that. And so if there is a statistical significance, what we're also saying is we're rejecting the null hypothesis. Recall last week we said that the null hypothesis is what the researchers set up to disprove, right? And if you can disprove the null hypothesis, what you're saying is whatever else is left over, that's likely the explanation. And so what we're saying is when we have a p-value of 0.024 here and a threshold of 0.05, we're saying there's only a 2.4% chance that the findings happen by chance. In other words, there's only a 2.4% chance that the null hypothesis is holding here. And so what we have to do is, because that 2.4% is less than 5% our threshold, we can now reject the null hypothesis as an explanation. In other words, we're rejecting the hypothesis that chance caused the differences between the two means. Now, in this situation here, we might have a calculated p-value, again given to us by SPSS, that came out to 0.32. Well, 0.32 is much, much higher than our threshold of 0.05. And so now we're saying is really, yeah, so to summarize, when our calculated probability, again, this is the value that SPSS gives us, right? If it falls below less than 0.05, if that's our threshold, then we reject the null hypothesis, right? We say we actually believe that there are important differences between the two populations or the two means that we're testing, right? And the findings are statistically significant. If SPSS gives us a probability level that is larger than 0.05, for whatever statistical test it's running for us, then what we do is we fail to reject the null hypothesis. Translation, although it's not technically correct, we accept the null hypothesis, right? We still don't know whether there are important differences between the two populations. In our case, we're measuring the two sample means, right, to reflect the population. And so we say that there is no statistical difference between the findings. The findings that we saw here likely happened by chance. Just as an aside here, notice that we don't use the term "we're going to accept the null hypothesis" when we believe it to be the case. I know this is a little bit of semantics here, but to say that to accept the null hypothesis is tantamount to using your statistical test to prove that the null hypothesis is true, and you can't do that. You're still only showing that there is a high percentage of chance that the null hypothesis holds true. You're still not proving anything. So this is why in textbooks you'll see the term "fail to reject." Listen, on a test, for example, on one of your quizzes or in your writings, if you use the term "I'm going to accept the null hypothesis," I'm not going to take any marks off, because I know that you know that I know what you're talking about. Now, with any statistical decision, is there a chance we could have made the wrong decision, despite what SPSS tells us? Right? So if SPSS came out and said, well, here's your calculated p-value, it's 0.013, and your threshold that you set was 0.05, and 0.013 is less than 0.05, and so I'm going to reject the null hypothesis and say there's a statistical difference, right? Could I have been wrong? Could I have been wrong in my decision? Remember, this is all about probability, right? There's still a chance I could have made the wrong decision. Conversely, can I also fail to reject the null hypothesis when we should have rejected it? And the answer for both of these is yes. There is a chance that in our decisions that we make, we could be wrong. There are two types of errors that a researcher can make in this regard. And the first one is what we call a type 1 error. And this is the rejection of the null hypothesis that is actually true. You've concluded based on the findings that the intervention was responsible for the difference in the scores observed. And you've got every right to do that, especially if your SPSS p-value, the calculated one that SPSS gives you, is much less than your threshold value. But sometimes, and this is a very small chance this could happen, sometimes, unknown to you, the intervention had nothing to do with the differences in the scores, despite what SPSS said. Remember, SPSS is only telling you the probability, right, that the findings happened by chance. There's still that small chance they could have happened by chance. And you say, well, that's pretty small for me, I'm going to reject that. Conversely, you may fail to reject or accept a null hypothesis that is actually false. In other words, SPSS comes out and says, yeah, here's your calculated p-value, it's 0.08, you set your threshold at 0.05, because the calculated p-value is larger than your threshold, you make the decision to fail to reject the null hypothesis, or to say, yeah, the findings that we see here actually happened by chance. But in reality, and again, this is unknown to you, there really was a difference. Your intervention really did work, but you said, no, the intervention didn't work. And chance is what caused the difference. But in reality, again, this is going to be completely unknown to you because you're never going to know. You actually made what we call a type 2 error, where you said chance caused, right? We think chance is responsible for the differences that we see and not the intervention. But in reality, it was the intervention that was responsible for the differences that you saw and not chance. To put this into tabular form here, I'm not sure if this table helps. I found it helpful once I figured out what was going on. This is a cross tabulation here where we've got two things. Let's look at the top line here. Here's the investigators. Let's look at the column here. This is the investigator's decision. So the researcher is going to make a decision. The researcher is either going to reject the null hypothesis or they're not going to reject the null hypothesis, right? So if the researcher rejects the null hypothesis and the null hypothesis is actually true, the investigator makes a type 1 error. If the researcher rejects the null hypothesis and the null hypothesis is false, then the researcher makes a correct decision. Again, conversely, if the researcher says, hey, I'm not going to reject the null hypothesis in this case, and the null hypothesis is true, that is to say chance caused whatever the findings were, then the investigator makes a correct decision, right? If the null hypothesis is false, for example, and chance wasn't responsible for the findings, but the researcher comes along and says, I'm going to reject the null hypothesis, then what the researcher is making here is a type 2 error. Before I go here, notice that this is again one of the weird things about doing research. You know, researchers are not omniscient. We're not God, right? Only God knows. Just like God knows the true score, only God knows the real situation of what you've actually done here. Okay, so the real situation is never going to be known to the investigator. The researcher can only make decisions based upon the probability of things occurring, right? And this is the risk side of research. And this is why we try to minimize risk all along the way. We try to minimize the risk of making the wrong decisions by having very robust methodologies, by having instruments that are highly reliable and highly valid, right? Then by having sample sizes that are robust enough to detect a true difference, right? We're trying to minimize that standard error score. So when we actually make an inference from a sample, we're actually making a correct inference. So we never really know for sure that we are committing a type 1 or type 2 error, right? This photograph of this fellow here, this is pretty much me in terms of almost my entire academic tenure. I was always scratching my head. What really? We never know for sure we're committing a type 1 or type 2 error. Yes. You're never going to know. Why? Because you're not God. That's why. But what we can do is take steps to decrease the probability of committing one of those errors or both, right? And what might be these things that we can do to decrease this probability? and I mentioned this before on the previous slide, here it is in script form. We can do all kinds of things, right? We can have robust sampling methods, right? Including sample size considerations. Is my sample size going to be large enough? We talk about the methods in terms of validity and reliability of our measures, all these things. And sometimes we accept and we hold on to these levels of probability that we select a priori or before the fact. Again, this again reduces the bias of the investigator, right? If you don't have a threshold set ahead of time, that's to say, well, here's our threshold of 0.05. This is what we're going to run with. If you don't do that, then the researcher's got all this latitude to say, well, I think the difference is big enough. We're going to say that there was a significant difference here, that our intervention really worked. Now you're simply working with the raw numbers. When you throw in your levels of threshold of statistics and take into account variability, now you're putting in these added checkpoints where when you make a decision, it's highly likely that you made the correct decision. So here we go. Inferential statistics, this is what we're doing now, right? Inferential statistics can never tell you for sure whether you have made an error, but they can tell you how likely it is that you made one, okay? So you're never going to know. Yeah, I might have made an error, but what you can come back with and say, yeah, the chances that I made a mistake are really, really small, right? So if the likelihood that we've made an error really is the alpha value that you set up in the first place, right? So for example, when you set up your experiment, you might say, well, I'm going to go with 0.05 as a threshold. I want to see if there's a difference between the means, and I'm not going to accept anything less than a 5% chance that it could have happened by chance. Anything less than 5%, I'm going to go with this. And so my chances of making an error that way are really small. Less than 5% chance I made an error, right? In some cases, you might even want to go a little bit further. You might go, I think for this experiment, we want to be pretty darn sure that we're finding a difference. And so we're going to set our alpha value at 0.01. That is to say, I'm going to accept less than a 1% chance that the findings that I see happen by chance. That's a much tighter range now that you've set up. If you want to be absolutely sure, well, pretty close to being sure that you made the right decision. And so to summarize this section, okay, this is stuff that we already know, but we're going to now, we've added a few layers to it here. Statistics work to disprove the null hypothesis, right? If we can do this, then this leaves the research hypothesis, whatever that intervention is, as the reasonable alternative to explain the findings. To do this, however, we have to set a level of risk to reject the null hypothesis. And conventionally, in the literature, almost every single article you're going to see, right, especially if the researchers put it on there, sometimes they forget, believe it or not. This is what reviewers of journals do, that they actually will give feedback. Hey, what's your level of significance? I've caught that before when I've reviewed journal articles. Conventionally, this is set at 5% or 5%. You'll see it as 0.05 somewhere in the literature. It'll be a statement. Level of significance was set at 0.05. That's what they're telling you, right? When the findings show up in the results section, you're going to see the probability values expressed as p less than, right? So a p less than 0.05 means there's less than a 5% chance that the findings that you see there happen by chance, and most likely they happened because of something else. And when this happens, we say that there is a statistically significant difference or a statistically significant association between the two variables. Whatever those tests are, right? We run all kinds of tests. I'm just talking about difference tests and association tests for the time being. And there's always a chance that the researcher, despite whatever they've done, when they make their statistical decision and their conclusions, they've made a mistake. And so the two types of mistakes that you can make are: one, the type 1 error, where the researcher rejects the null hypothesis when it was actually true, right? In other words, you're saying that you thought that your intervention caused a difference between the means, but in actuality it didn't really, right? And there's the type 2 error, when the researcher fails to reject, or as we call it, to accept the null hypothesis when it was actually false. The researcher says, yeah, the differences here likely happened by chance, and it didn't happen by virtue of our intervention. And really, in reality, it really was your intervention that actually caused the difference. The level of threshold, again, sets the probability of you making a wrong decision. And the smaller that is, right, the less chance that you are going to make a mistake. Or not you, I'm talking about the researcher. Conventionally, the type 1 error is considered to be more more of a problem making that error than the type 2 error.